Okay, so about the screening designs, most of the time we are interested in determining which of many factors that we have they are important and should be included in our study. Fractional factorial can be applied. We would prefer them if the design allows it, right? Usually resolution 4 design is desired, but what about if we don't have, like, we can't afford to have like resolution 4, like we would have resolution 3, for example. Another class of designs that we have, that we call them Plackett-Berman or PB, it was developed specifically for a screening purpose that we are going to learn in this video. And most of the time we have it for the resolution number 3 designs. We can have it for resolution 4 when we are working with PB, but we would, at the end of this video, you are going to see that we'll do something else with it. But let's say this is the resolution 3 designs, which can be inconclusive. For example, variable A is significant or A is not, but the two-factor interaction confounded with variable A is, like the interaction is significant. Variable A could be confounded with a strong negative interaction and they cancel each other. The PB designs are unique. The number of the runs may not always be represented as 2 power n. So if there are non-geometric designs, the number of runs often appears as a multiple of 4. Like, for example, if we have 6 to 7 factors, we would do that in 8 runs. If we have 8 to 11 factors, we would do that in 12 runs. If we have 12 to 15 factors, we are doing that with the 16 runs. So this is the PB designs that we would do. We have a design generator table, like the design generator table that we had before. So look at this one. What are we going to use? What are we going to get from these screening design generators from this table is that you see these positive and negatives. Like, for example, the number of the factors that we have and the number of the runs for that factor that we have. We are going to use these, like move these positive and negatives to our design generator table. So do you remember that I said that the tables that we make, and we say A, B, C, D, and then negative and positive of all of those, we said that those ones, we call them design tables. So to have with the screening designs, because it's not geometric, what do we do is that for deciding which one is negative and which one is going to be positive, because so far what did we say? We said that, okay, let's have like the negative, positive, 2 negative, 2 positive, 2 negative. So I mean that first column and the second column and the third column, like 4 negative and 4 positive, right? But here with the screening design, what are we going to have? Our hands are not like open to just put like one negative, like negative, positive for the first column, negative, positive, and then 2 negative and 2 positive. So we need to obey this table for it. So I would recommend that you would, it would be a good idea if you just print this table as well, because we are going to refer to it whenever we're working with the screening design. So look at here, we have like positive, positive, negative, positive, positive. It's like that. Here we have it vertically, and in an example in the next slide I'm going to show you, we just show it, we would move it like horizontally. Look at here, these are the steps. I start with the column from the table of screening design generators as first row. So it's like that, the first column, like the column that you get from this, so maybe it's this column, we don't know, one of these columns. It depends on the number of factors and the number of the runs that you would have. You're gonna choose the column and then consider as you like move it, and you would consider it as your rotate it, and you would have it as your first row. And then make your next row which is obtained by taking the first sign of the preceding row, like the row that you had before, putting in the last position and shifting all other signs to the left by one position. And this one is the typo, is the next row is obtained by taking the first sign. So after all cyclical arrangements, add a row of negative signs on the bottom. Let's see an example of it. Look at here. I have A, B, C, D, E, F, G, H, J, K, L. And then I have 11 factors. So what are we going to do is that I have 11 factors. I'm going to write down the 11 factors here. Then I would go to the screening table and I would see that, okay, so when I have 11 factors, I would need 12 runs. So I'm going to write down the 12 runs. This first row is the, look at here, what do you have? Positive sign, minus, positive, like negative, positive, 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 negative, 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 positive, negative. Let's go back to the design generator. Look at here, positive, positive, negative, positive, 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 negative, 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 positive, negative. So it's exactly the same as the one that we have here. So we had the 11 factor, 12 runs. We said that, right? So here we said that whenever we have like 6 to 7 factors, it will be 8 runs, 8 to 11 factors, it will be 12 runs. If we have 12 to 15 factors, it will be 16 runs and etc. However, we can have it, we can decide with this table as well. So then what are you going to do is that, look at here, this negative sign, it's going to come here, and then you are going to shift all of these one to the right. For example, you would say this positive is going to come here. This positive sign is going to come here. This negative sign is going to come here. You see that how it goes to the diagonal? And then the positive is going to be like the same signs that we have, right? And this negative can be. The next row, you're going to shift it one more time. So it's going to be the first, this positive come here, and this negative here, negative, negative, positive, 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 you see? So we would go all the way to the 11th, and the last, just the last column, sorry, the last row, we're going to write down all negative. Like all of these ones is going to be the negative one. And then we're going to find out the effects, the combination of them and all of them. The rest is going to be the same as they had before. So what I might ask you is that I might ask you to give me this, like for a smaller version. Give me the design matrix. So this is going to be your design matrix. You have all of the negative and positive sign of it. For the PB design, it can be modified by including the foldover to yield a design which is of resolution 4. So if you have, we said that one we use the screening and PB design when we have resolution 3, right? But we can have a foldover to yield the design which is of resolution 4, so make it a little better. Then conclusions about main effects are likely to be correct. A full foldover is like a mirror image of a design. So the positives become negatives and the negatives become positive. The next page, we have an example of it. By using a foldover, we sometimes gain a bonus factor. We may resolve a single factor. Adding a center points allow us to calculate an error estimate for the ANOVA. So the same thing here, if we want to find out the error estimate in our ANOVA table, even with the scaling design, we can add the replicates as we had before. Before you start adding foldovers, check fractional factorial scenarios. You may get more info about it. The single factor column foldovers can be used for the partial foldover. And we have an example in the next slide. If you want to go after a specific factor, like you want to resolve a specific factor. Now let's look at it. This is the simple factorial. So I had the negative, positive, right? And then negative, negative, let's say positive, positive. So we're just talking about the concept of the foldover, and that's all we need to learn for this chapter. So the full foldover is that you would say, okay, I have like whatever, like for A, whatever negative sign that make it positive. It's like that you put a mirror. So the It's going to be, here was negative, positive, negative, positive. So here it's going to be positive, negative, positive, negative. And then the full fold over, when we say full fold over, we would have a mirror for B as well. So negative, negative, positive, positive, it would be positive, positive, negative, negative. We can have partial fold over on A, and then we would have, like, instead of the negative, so we would just fold over A. We don't do anything for B. So it would be positive, negative, positive, negative, and then negative, negative, positive, positive. So what we want to know here is that we just want to know that, okay, so we can have, like, so what I would ask you is that, okay, so for example, the screening design, how can you generate then design metrics for the fold over? I wouldn't ask you any question like on the assessment of the quizzes, because I just want you to hear that here, that, okay, so we can have like the partial for these signs, and then you're going to put these signs on your design matrix, and the rest is going to be the same. Like you would have the effects and the everything is going to be the same. Like calculate the effect, calculate sum of a square, and calculate the ANOVA table. If your ANOVA table, you want to find out the error, have some replicates to find out the mean square of the error, and then find out the F observed, and with the F observed, say which one are the significant or not. So for that design matrix that we have the negative and positive signs, when we had the full factorial and fractional factorial at the beginning, it was geometric, so we could do that. When we have resolution 3, we would go with the PB screening design, with the screening design table that we had. If we have like if you want to have like the resolution 4, we would use the fold over, and we can get the resolution 4. Here, this is a good table, like good numbers. Look at here, this just we are wrapping everything. So the number of factors that we have, let's say we have 6, 7, 8, 9, up to like 20, for example. For the factorial ones, this is the number of the factors that we would have, number of the experiments that we would have for the full factorial. For the fractional factorial, for the resolution of the greater than or equal to 5, we would have the number of the runs that we would have, it's going to be like this. And then for the PB with fold over, then we say the resolution is 4. This is going to be the number of runs that we have. So this is just that we don't need to memorize it. Everything is the open book and open note. But I think this is a good one, like for later when you want to, for example, know how many runs would be the optimum number of runs that you would have. So you had a question, you asked me to email that, okay, Lena, how can I decide that how many runs I would have, like how many experiments I would have? So this is based on the method that you want to go. This is the optimum number of the runs that you would have. There's no way that you would go with the 4,000, right? So definitely you want to go with the PB, for example. Even 256 is a lot. Okay. So here's the concept map. So we learned about we had the intro to fractional factorial design, the effects of them, the base design of the 2 power 3, and the confounding pattern, design resolution, the table of the design generator, table of the screening design generator, and then we learned about the screening design or Plackett-Berman designs that we had in chapter 7.